Hi, welcome to the video. In this video, we will implement quantum support vector machines using Pennylane and scikit-learn. In the previous part, in this video, we have already seen the theory behind quantum vector machines, and now it's time for the practical implementation. Okay, so let's start with the implementation part in the second video. And obviously, we'll first start with the installations. So we just need to make one installation here, which is Pennylane. Google Colab comes with everything else that we need. Okay, let's get started with the imports. And first thing we would need is NumPy. Pretty simple. And the second one is obviously Pennylane itself that we just installed. Use just UML because it's mostly used for quantum machine learning. It's popular for quantum machine learning. And okay, so other things that we need are from sklearn. And the first thing we will import is the dataset, our dataset, which is the very popular iris dataset. Then the second import is for pre-processing, which is max absolute scalar. The next part is from model selection, which will be train test split. That will be used for obviously to split our dataset. Then the most important import is the SVC class, support with the classifier class from SVM. Okay, and then the last one would be just the metric. We'll use accuracy score to judge the model we built. Yeah, that's pretty much we need. Let's run it. Okay, let's see. We can start with loading our data. That is pretty simple. We just need to run one line, x and y as 2. Okay, let's run this. So this is the popular iris data set, and we have, and so for our x, we have four features. That is the petal length, petal width, sepal length, sepal width, and for y, we will have three classes, which are three different irises, right? So, okay. Now, just the way I mentioned, we have actually three classes, but we just want to reduce this to binary classification. And since there are 50 samples for each class, if we just take the first 100 data point, first 100 samples, then we will naturally reduce it to a binary classification problem. So let's go ahead and do that. And so first 100, and this will be first 100 as well. Okay. The next part would be to first split the train and test data set. Let's go ahead and do that. Train test split. That would take X, Y, and the train size would be 0.5, and there's a reason to it. And then we can also give a random state, I feel. Random state can be, say, 42. Yes. Shuffle is already 2. So, yeah, we can just run this. Okay, so we've got our train and test split. Now comes the time for pre-processing. So let's do the pre-processing part with our uh, scalar, the max absolute scalar that we have imported. And this is defining. And then we will first transform our train dataset, which is fit transform. Fit transform the train dataset. Then obviously we need to do the same for the test dataset as well. And this will be just transform because this is obviously our test dataset. We don't want killer to fit to this. So we have done the fitting part, transform part, and one last thing that I think we should do is clipping the test data because it is transforming it. So what we can do is pass this test and make sure it all the values are in the range 0 to 1. All right. Yeah, so that's it. So this the pre-processing part is done. Now comes the quantum part. So let's revise a little before we dive into this. Okay, so let's open this. Okay. So this was the kernel function from that I explained in the previous video. So what we need to do here is define this circuit file that would take this xk, right? And then we would also need to define a circuit file dagger that will be just the the adjoint of this circuit. So that is just reversing the gates from right to left and taking the inverse. But so this is what we actually need to define, right? So let's get to Colab and see how that can be done. Okay, so let's now build our Qkernel. And the first thing we would need is obviously define the number of qubits that we will use. And that will be 4 because we have 4 independent features in our data set, right? And now the next part would be we need to define the device where we will run our quantum circuits. And since our data set is really simple, we will just go with the default device, which is default.qubit, right? And then we will define the number of qubits that this device will use, which is nothing but the number of qubits, right? Okay, let's run this. And now comes the important part, which is defining the circuit itself. And we do that using this Q node decorator in Pennylane, which takes the device, and then it will bind this device with the circuit that we define now. So we will define our circuit, the Qkernel circuit, and this will take obviously A and B. So this is like our XA and XJ, and it will compute the kernel for this. So what the feature map I'll use is very simple one, angle embedding. There are many else. There are amplitude embedding. You can also have your custom one, and I'll tell you how you can use your custom feature map as well. But let's just go with the default, the simple ones first. So I'll define the features. Wires would be range of number of qubits. All right. And then rotation can be X, Y, or Z. So if you want to use RX gates, you will go with X. I want to use RX gates, so I'll go with rotation as X. And this is so this was our circuit phi. Now we need to define the circuit phi dagger. And that is really simple. We can just do simply that using qml.enjoy. And now we can do the same thing inside it. So qml dot angle embedding. And features would be B here, obviously. Other things would be same. Y's would be the range of qubits. And the rotation will be hex because that's what we have used previously as well. And for the returning part, we will just return the probabilities, and that would be wires and range of number of qubits as well. Yeah, I guess that's it. So we can define this. Now let's get to the next part. Now, since our our actual SVC class needs some metrics. So for computing, the function that we would need to pass to SVC should take the two arrays and then compute for all entries JK for A of J and A of K. So the little part we did that we need to do still is this. So this will take the two arrays A and B, and now we will use our Qkernel circuit to run this on each entry of A and B, right? So what we can do here is we will return a numpy array, and we will since this is a metric, so actually we need to iterate on two of them, right? And okay, that will be because this will be A in A and B in B. And now here we can use our kernel circuit, right? And we can pass our A and B here. And we will just take the first entry because we are passing all the probabilities, but we need the probabilities of all zeros, which is obviously the first entry in this probability vector. So we'll just take the zero entry. And yeah, I think that's pretty much it. So the slight modification. And now it's the standard sklearn work. Now we can just define this as the support vector classifier. We can, as the argument of kernel, we can just pass the Qkernel that we just created. And then what we can do is we can just fit this to our X train and Y train, and I will train this. It might take a little time depending on your device. And once this training is done, we can then resume again. Okay, so training is done. Now we can just use the train model to get the predictions, and we can do that using the predict, the same way we do for all SQL models. And this will I will pass the test data set to this, and it might take a little time depending on the size of your set. Okay, so that is done. Now what we will have is just the accuracy score, so we can see how our model is performing, and I have less hopes for this because you haven't really done much. And okay, so the first one is Y true. It is actually Y test, right? Point 0.4. I obviously knew it won't work, and I'll tell you the reason for that. The first is the angle embedding, which is the embedding that we use. Is really angle embedding not so powerful. What people generally try to use is amplitude embedding. That's a higher space. It's usually what people use, but again there are advantages, disadvantages of it. Because amplitude embedding is a linear embedding. But yeah, and another part that I would like to mention is if you want to create your custom feature maps, then how can you do that? So just first define your feature map and in a Python function, the normal function that would take these features value and replace it with this QML.angle embedding. Then what you can do is just use this QML.adjoint over the function and then just pass your function, the same function inside this QML.adjoint, and that's it. Just that's it. You can use any custom feature map of your choice, and this will still work the same way I've shown you. So I hope I was able to help you with this, and if I found this helpful, you can share it with your network. If you get stuck somewhere, if you find some errors, let me know and you can work on this together. And the link for the GitHub will be in the description, so you can, directly get. Also, don't forget to check out the part one where I have explained the theory for quantum support vector machines. And there are other ton of material on the channel that you can explore for quantum computing and quantum machine learning. And until then, I'll see you in some other video, next video. Until then, take care.